Hey guys, welcome back to part two. So now we're going to be talking about comparing two different proportions and specifically hypothesis testing. So yesterday we showed you how to put that in the calculator as a two-portion z-test. But what we didn't actually talk about is there's some slightly different math going on where we're doing something called pooling. So whenever we're finding a p-value, it's based on the null hypothesis or the probability base of if the null hypothesis is true. And that's assuming that those two are exactly the same, but there's no difference between the two groups, just the difference in the sample size. And that would actually require us to pull the data together to find some weighted average. So that's what we're going to be getting into today. So will you snore when you're older? That's kind of the question that goes along with this. I think the book talks about it, so if you want to follow along with that, you can. It's also example 1 on your worksheet, so we'll be going through that together where I show you how all the math works. So the question is, are you more likely to snore when you're over the age of 30 or if you're under the age of 30? Now, I am 27 and I swear I do not snore, but it is possible that when I get older, I might start to snore at some point, which would be very, very sad, a sad reality. But as I live alone, I have no idea if I actually snore or not. But as far as I'm concerned, I don't snore. But yeah, anyway, so let's see if the data, what the data shows. So in 2002, a National Sleep Foundation study did a sleep study of 995 people. There were 184 that were under the age of 30, so 18 to 30, I believe, and then there were 811 that were 30 or over. Notice that it's not important for us to have the exact same size, where it's split like 50-50 between the two samples. What ends up happening is our larger sample will end up having a smaller standard deviation, but the smaller sample will have more variation because smaller samples vary more than large ones, which is okay. And all that, as long as they're independent, will be put together with the Pythagorean theorem of statistics to give us the standard deviation for the sum or the difference, which we're looking for the differences between these two, of two random events. For the people under the age of 30, they found a proportion of 26.1% of them snored, but if you were over the age of 30, 39.2% of them snored. So does it look like there's a difference between these two? Well, yes, if we subtract the two, the difference that we see, we're going to do the larger minus the smaller one, because we typically tend to prefer to work with positive differences, would tell us that there's a 13.1% difference between the proportion of people snoring that are over the age of 30 minus the proportion that are under the age of 30. So that's the correct way to interpret that. You don't want to say 13.1% more likely to snore, because that would actually be like 113% of the other one. So there's a 13% difference is the proper way of interpreting that. But that's a common misinterpretation. Okay, so do we think it's likely that, or possible that there really is no difference between the two? Is it possible we observed a 13% difference just because of random sampling variation? Well, if we look at our two individual standard deviations of 3 and 1.7, a difference of 13% is definitely going to be more than 3 standard deviations away from both of those, but that's not exactly quite how the math works. So what we want to do is we actually want to write our hypothesis. So we are going to do a z-test, so a two-portion z-test. In fact, you can pull up your calculator and get that out, and I'll show you how we do that. But so our null hypothesis is going to be that there's a status quo, or that there's no difference or no change, meaning that the difference in the proportions between people that are over than 30 and under 30 is going to be equal to 0. So that's how we would write it with symbols. If we write it out in words, in context, there would be no difference between the snoring rates among those two age groups. Now our alternative, we want to know if it's a one-sided or a two-sided test. So do we just want to see if there's a difference in general, or do we specifically want to see if it's more likely that you are to snore when you're older? So it makes sense. You could do a one-sided upper. You also could just do a two-sided test to see if they're different. On this one, we're just going to see if is there a difference between the rates of snoring between people in these two different age groups. So in other words, that there is a difference between snoring rates between the two age groups. If we want to say that you're more likely to snore when you're older, then we would do this would be a positive difference, because the older minus the younger would be positive. So then it would be a one-sided upper test, or one-tailed upper test. All right, so if we want to calculate our p-value is going to be based on the assumption that our null hypothesis is true. So if the null hypothesis is true and that there really is no difference between these two age groups, then what's the probability of observing a difference of the 13% that we observed? So basing on that assumption, well, if they really are the same, and there's no difference between snoring rates among any age groups, then the only difference is that we had a small sample of just pooled Americans and a large sample of pooled Americans. So notice now we're not referring to them as under 30 or over 30. Now we're assuming that if the null hypothesis is true, it's just a large group of Americans and a small group of Americans. So what we have to do is pull those together, which is like finding a weighted average, which we talked about before in the probability unit. But basically we had 48, we would add all the people who snored. So we had 48 who were under the age of 30, and we had 318 who were over the age of 30. So a total number of people that snored would be 366 out of a total number of people who were part of our sleep study, which is 995. So our total pooled proportion is 36.8 Americans. Now, what's kind of cool is this information is actually already done for you in the calculator. So I'm showing you how the math works so you kind of get a good understanding of hopefully how this works. Because if you notice, like actually putting this in the calculator is not really that hard. But the hardest part of statistics is interpreting what the calculator is telling you and being able to write those sentences, putting it in context and interpreting the data, knowing when to reject the null hypothesis and all that stuff. So it's important that you do understand the math and the formulas and kind of where it comes from, but also how to put it in the calculator. So we're going to do a 2 proportion z-test. We have 48. I'm going to do my larger sample first. So that's going to be the 30 and over. So 318, not the largest sample, the larger proportion, because we want a positive difference between the two. So 318 over 811, and then 48 over 184. And I want to see if the first proportion, which is the older, minus that, and I want to see if they're just different. So two-sided test, then we hit calculate. So a lot of information here looks intimidating, but break it down. So our z-score is 3.3 standard deviations above the mean. Now, anything that's beyond 2 standard deviations is probably what we normally would consider unusual, but now we can actually use a p-value to see specifically how unusual it is. So our p-value, defined in context, would say that if the null hypothesis is true, meaning if there is no difference, then they're probably observing the difference that we saw of 13% among 2 sample sizes of a small group of Americans, pooled Americans, and a large group of pooled Americans would be 8.6 times 10 to the negative 4th power, which is basically 0.000 with 3 zeros, 8, which is less than 1%. And so even if we had a strict alpha of 1%, it still would be beyond any reasonable alpha, which would be statistically significant enough for us to reject the null hypothesis in favor of the alternative, stating that we believe there is a difference between the snoring rates of the 2 different age groups. Okay, p-hat1 and p-hat2, these are going to be our sample proportions for the percent of people who snored over the age of 30 and the proportion that snored under the age of 30. That looks right. And this p-value here, that is actually the pooled proportion. So we saw that before. You didn't know what it was, but that's what it is. So the calculator actually will pull it together for you, which is nice, so you don't have to do it by hand. But it's the average, but it's not just the average, it's the weighted average. If we take the average of 26.1 and 39.2 and we add them together and divide by 2, that's assuming that they're weighted the same, but they're not, because one of the samples is clearly larger than the other. So that's where we get the weighted average and averages altogether. So it'll do that for you, which is kind of nice. And then it'll tell you the sample sizes for the first sample and the second sample and all that. So all that information's there and we're good to go. So the question that we had are if they were really the same, then that means on average 36.8% of Americans snore. Then we had a young group that of a smaller sample of 184, which had a sample proportion of 26.1. Now, because it's a smaller group, it is more volatile, more likely to vary. Because samples vary. All samples vary. Smaller samples vary greater. And then the larger sample proportion, if you notice, is going to be much closer to the pooled, which would be if the null hypothesis was true. That would be the overall average proportion for people that snore. So is this unusual? Is this total thing altogether unusual? Well, we don't like add their z-scores. We actually do 2 separate events, which is where we get the Pythagorean theorem of statistics, like what we talked about yesterday. So notice now these are pulled together because I'm basing the p-value, the calculation of the p-value, based on the assumption that there's no difference. So it's just a large group of Americans and a small group of Americans, not basing them based on their age. So if we have our pool for this one, that would be the proportion out of the large sample. This is our pooled proportion out of the small sample. This is how you calculate 2 different standard deviations based on those. And then if they're independent events, and they should be, young people snoring and old people snoring, this should be unrelated to each other. And then as long as the people that we sampled weren't actually related to each other. So if you like did groups of families, then that probably is going to have some issues because it could be, I suppose, genetic. I don't know. But that would give me a pause for consideration. So basically we do the a squared plus the b squared is equal to the c squared. We do our Pythagorean theorem of our standard deviations, and that will give us our total, our new pooled, the new standard deviation for the sum of two different groups of pooled Americans in this general. So a group of 811 Americans plus another sample of 184 Americans in this case. All right, so then our final thing is we observed a difference of a positive 13%, which would be way off of here. And we were expecting 0 if that was actually true, with a standard deviation of basically 4%, I believe. Yes, standard deviation of 4%. Is that what it showed on the other one? Yeah, 4%. So what's the probability of that occurring? Well, if we look at our calculator, the z-score was 3.3. So it's 1, 2, 3, 3.3, somewhere about there. With a p-value of basically less than 1%. Our p-value in this case was 0.0008, which is less than 1%. Okay, so let's revisit our null and alternative hypothesis. So our null hypothesis said that the difference was 0, that there's no difference between snoring rates among the two age groups. The alternative said that there was a difference. So if there was no difference, then this is our distribution, right? It would be centered at 0 with between those two pooled samples of a larger group and a smaller group. This would be the standard deviation that we'd have. So it would be 1 standard deviation, 2 standard deviation, 3. Whatever we set our alpha level to, of 5% or 1% or whatever that is, that's going to be the probability of our type 1 error, which type 1 error would be that there actually was a difference and we failed to recognize it because type 1 error would be that we thought there was a difference when there actually wasn't, and that was just because of it was in the top 5% of sampling variation, which can happen specifically 5%, 10%, or 1% of the time. So we probably would have selected an alpha level of 5%. So did the observation that we occurred, a difference of like 13%, was that actually, was that a part of the top 5%, or did it actually, was it a measured difference? So that actually depends on what the actual true proportion is. What's the effect size? So how far off? So let's say that there is actually a difference and it's not 0%. You are more likely to snore. Well, if that is actually 13%, let's assume that it was 13%. I don't know. Let's say maybe it was only 10%. Maybe there's only a 10% difference of snoring rates between those over 30 and younger than 30. So that's the effect size. There's an actual difference of 10% between the null hypothesis and the actual, difference that we see between the two. Then the power of the test would be the ability of us to correctly reject that, to be able to recognize that. So we would have to have percentages that were above, well, depending on where our alpha level is. So if we had an alpha level of 5%, then this would be the power of the test. Looks like about maybe 40% or something like that. So 40% of our samples would have been able to detect that. Now, so let's say that the actual proportion, the effect size was actually, let's do 13%, which was our sample. But let's say that's actually what it was, the true difference between the two populations, proportions. So then the power of our test to be able to detect that difference looks like maybe around 95%, meaning because it's such a far difference and because our sample sizes are there's such a small standard deviation of only 3% or 4% because we have fairly large samples, then we were able to detect that 90% of the time. So 90% of all samples, they would all fall within this range here, 95%, and we would have been able to correctly, beyond the significance level, be able to reject them. So it looks like we'd have a false positive rate of 5%, which was our alpha level, and our false negative rate of maybe about 2.5%, which would be when we failed to detect the difference because of just normal sampling variation was in the bottom 2.5%, which is below our significance level. So hopefully all that makes sense, and it's really important you guys understand how to interpret this information, which is really the hard part of stats, not just putting it in the calculator and getting the information, but knowing how to interpret that to make your decisions and understand what type of error you made and what's the consequences of those errors. All right, so our next thing is once we say we believe there is a difference, now what we want to do is we want to create a confidence interval. Now, there's a slight difference. Now that we say there is a difference, we're no longer going to use this pooled Americans thing. If we believe there's a difference, now our P hat and our Q hat are going to be, for P1 or Q1 hat, whatever, are going to be based on what our best estimates for what those differences actually are. So we're no longer going to be using the pooled information. The pooled information is only when we're doing a p-value, which is based a conditional probability based on the assumption that the null hypothesis is true and that there actually is no difference. Now that we believe there is a difference, we use the actual values, which are from our sample proportions. So no big deal. Let's go ahead and put it in the calculator. So we'll go over to test. We're going to do, I think it's B, as in Bravo. So 2 proportion Z interval, and we already have them together. We'll do a 95% confidence interval. And then there's our interval. Now, how do you interpret that interval? So we're 95% confident that the true difference in proportions between people snoring over the age of 30 and under the age of 30 is between those two values. So it's between anywhere between, say, 6% and 20%. So is the next question we would have is 0 contained in that confidence interval? No, this isn't. Our interval is entirely above 0. So then the next question is, based on this interval, did we have enough evidence to reject the null hypothesis? Which is, do we think that it's possible that the difference is actually really 0? Well, no, we think it's at least 6, right? It's anywhere between 6 and 20%. We're 95% confident that it is. And so we would have enough evidence to be able to reject that claim. Now, if we did a 95% confidence interval, it means there's 2.5% on both ends of the tails. So that would give us an alpha level of altogether 5%. If it was two-sided, if it was one-sided, it would be an alpha level of 2.5%. Okay, so we have our different standard deviations here. And then we basically do the Pythagorean theorem of statistics again, but with these standard deviations. Notice the standard deviations don't actually change that much between using the pooled data and using the unpooled data, I suppose the original data. The reason for that is because the standard deviation is mainly affected by the sample size, not the actual proportions themselves, but it is a difference, and that's how the calculator is calculating it, in case you're curious. So we said from our sample, our best estimate is the samples, the largest samples that we had, which suggested there was a difference of 13.1%. The standard deviation between these two different samples of the large and the small sample of over 30 and younger than 30 is going to be basically from the Pythagorean theorem of statistics. So we take a variation of the older than 30 and the variation of our sample of 184 that were under the age of 30, and then we add the variations together and take the square root to get the standard deviation for the two independent events, which are our two groups of those over and under the age of 30 with those respective sample sizes, which gave us a difference of, instead of 3.9, now it's 3.66% for our standard deviation. Now our confidence intervals, we take our difference in our two samples, which was this 13.1%, plus and minus our critical value times our standard error. Now our standard error, again, we know it's error because it's based on our sample proportions, and that's probably not what the actual true proportions are, but no one knows the true proportions. That's why we call it standard error. There's nothing wrong that happened. It's just we know it's not exactly right. But it is our best estimate. So we're going to take our critical value of 1.96. That tells you how many standard deviations we have to go out in order to capture with 95% confidence the true proportion and 95% of all confidence intervals. So 1.96 times this critical value, or times this standard deviation, will give us the margin of error. We add and subtract it to both sides. It'll tell us how far we go out on both sides, which will give us our confidence interval graphed out here of anywhere between 5.9, which is this value here, and basically 20.3, which is this value here. So graphically, you can see where our confidence interval came from. It's pretty thorough. I don't usually go into all that detail, but hopefully you're understanding what's going on with confidence intervals. So our conclusion, with a p-value of 0.0008%, so basically 0.08% if we're doing percentile, means that if the null hypothesis was true, the probability of observing the observation difference of 13.1 between those two groups of Americans at that point the pooled Americans, would be only 0.0008, which is less than any reasonable alpha. So we have a statistically significant evidence to be able to reject the null hypothesis in favor of the alternative hypothesis, which is to state that we believe there is a difference. Once we say that there is a difference and we went with the alternative, the next logical question would be, what do we think that difference is? Well, surely it's not going to be exactly 13.1%. That was just our best estimate. So that's where we have to add the margin of error to there, which gives us a confidence interval. We believe the true difference between the two, which, notice I'm not using the hats anymore, but I should have used hats on those. Oh, I did right here. Yeah. So the true proportion difference in the population proportions between old and young is anywhere between 6% and 20%, or 5.8 and 20%. So the last question I want to mention is that I know there's like this thing where everyone thinks that men are more likely to snore, and maybe that's true, and that would be a really fun study to look at, basically breaking this up by men and women. See maybe if women are even more likely or have a larger difference between their proportions of age to be more likely to snore when they're older or whatever. But let's be honest, and it's like men never asking women how much they weigh, you know, that whole thing. It's kind of funny. My sister, she's due at any time with my third niece, which is really exciting. And so I was like this close to asking her how much weight pregnant women are supposed to gain, like, and you know, in order to carry a healthy baby to term or whatever. But I was smart and I didn't ask her. Instead of I asked my mom, who's not pregnant, obviously, who has had 7 children, so she knows things about pregnancy, you know, more than I do. But anyway, so I asked her, and so she answered between 30 and 40 pounds they're supposed to. But it depends on what your starting body mass index is. So some women actually lose weight because they're eating healthier for the baby and stuff like that. But if you're at a low BMI or something like that, you're supposed to gain from a healthy weight to a healthy through a healthy pregnancy through 40 weeks or whatever. It's supposed to be anywhere between 30 and 40 pounds. But my sister did actually answer the question. But so you never ask whether or not women snore. But let's be honest, if guys are being honest, this happens too, by the way. But no, sorry, women don't snore, they purr. That's right, they purr. So anyway, kind of funny. I think it's funny. That's why I told you. I hope you guys are laughing too. Or I'm just laughing at myself at midnight. That's my life. It's great. Anyway, so there is a difference. We think the difference is somewhere between those two. So the next part that we could see is we're actually kind of answering questions that we started out asking at the very beginning of the year with contingency tables. So do you snore? Yes or no? What age group are you in? That's the contingency table. Basically, it's sorting data across multiple variables. The variable of 2 questions we're asking, your age and whether or not you snore. And then at this point, we could break them down to the marginal distributions, which would be what we had, basically that out of this and this out of that and that out of this and that out of that. Anyway, that's how it was done. And then you could graph it out. When we graph it out with a segment and bar chart, what we're looking for is, are these two the same, or are they close enough that we think they might be independent? So we said like 5% difference like could be independent, but really we need to be looking at a p-value. But we'd had to know how to do the statistics to find the p-value, and we didn't know how to do that back then. So now we do. We're finally answering that question of what do we consider statistically significant? What would be at what point do we say that there's enough evidence of a difference between the two? So even though these look fairly close to each other, because we had a large enough sample size, we actually know the p-value is 0.0008, which would be statistically significant. Okay, cool stuff. Other ways that we graphed out categorical data, by the way, in case you were curious, was with pie graphs or pie charts, and also segmented bar graphs. This is the only way that we compare and break down the total distribution or marginal distribution based on some sort of group. So we actually have what we call, a conditional probability. So based on whether or not you lived or died, what was the conditional breakdown for that of whether you live or die? What's the breakdown of class? Now we would expect these to be about the same, and they're obviously not. So there appears to be an association. Now if we did the same thing for survivors and the non-survivors, which is really sad, but then we would expect those breakdowns to be about the same too. So we use segmented bar charts and pie charts to basically test for visually whether we think they're independent or if we think there's evidence of an association. But we would actually use 2 proportion Z test, which you can imagine us doing here, to test to see if what's the p-value, and if we think it's statistically significant enough for us to reject the null in favor of the alternative, saying that there is an association, that there actually is something going on, that you're more likely to survive or to die depending on your class. It's kind of cool. So side by side here we have the Titanic passengers and the survival by class. We'd expect those to be about the same if they actually were independent. Okay, so polling. For polling, basically we take the total number of successes from our first group plus the total number of successes from our second group and add the totals there. So basically you pull it together. The calculator does it for you, but it's a weighted average is what it is. The standard error for the polling is basically going to be the variation from our first sample, which we're using the pooled samples, and then the p-pooled as well, because it's basing all of this on the assumption that the null hypothesis is true, meaning that there really was no difference. The only difference was in the sample size, and that's why we're pulling them together. Okay, so variation of the first pooled group plus the variation of the second pooled group, just of different sample sizes maybe, and then we take square root of all that to get the standard deviation. So that's what it looked like with our actual numbers, in case you're curious. So let's get started with the assignment. A lot of stuff. This is really the last new thing that we have is pooling data. We'll do another example of it on Thursday or whenever you're watching it at home, and then we'll do a review of the unit before we take our practice test and take the test in class next week. So the video tomorrow should be much shorter, and the one after that as well. Okay, so we're pretty much done with the unit. We just got some review days. Number 20, the Journal of American Medical Association reported the experiment intended to see if the drug Prozac could be used as a treatment for the eating disorder of anorexia nervosa. The subjects, women being treated for anorexia, were randomly divided into two groups. Of the 49 who received the Prozac, of those 49 who received the active drug Prozac, and 35 were deemed healthy a year later, compared to 32 of the 44 who got the placebo. So part A, are the conditions for inference satisfied? So the randomization condition, are they two randomly groups? Yes, so they were randomly assigned to their treatment groups. They're not randomly sampled, these are experiments, so it's important that they're randomly assigned to the treatment group. So we can't let them choose if they want to be part of the placebo or part of the active group. So we're good. We have randomization here, which is going to control for any lurking variables or outside sources of or variables of confounding as well. So we're good to go. So the treatments were randomly assigned. That's it. Independent groups. Now, just like the Pythagorean theorem is based on the condition of the two sides being perpendicular or it being a right triangle, we have a condition as well for the Pythagorean theorem of statistics, which is that the two have to be independent of each other. So if one of the groups, so basically they have to be two independent groups. Now, they are going to be independent because of the random assignment of treatment groups. So that should meaning if there was success in the placebo, that should not affect whether or not there's success in the Prozac. So that's the whole point of the control group, is to make sure that the groups are independent. Okay, so the groups are randomly assigned, so they should be unrelated to each other. We're not letting people choose the group that they want to be in. That would cause some issues. All right, just like we don't let people choose to volunteer for our surveys, voluntary response bias, right? All right, success failure condition. Do we have at least 10 who did and 10 who did not were considered healthy from their disorder, recovered from disorder? I don't know how you state that. We did. We had 12 that didn't, and over here we had 35. Yeah, we had 14 that didn't. So that's true. There are at least 10 that did and 10 that didn't for both groups. Find 95% confidence interval for the outcomes. Okay, so those are our two proportions there. We're just going to put this right in the calculator. It makes it a lot easier. So stat arrow over to test. We want to do a confidence interval, which is B as in Bravo. Okay, so we're going to do Prozac minus the placebo. We're assuming that we should have a greater recovery rate, I suppose, for Prozac over the placebo, right? So we're going to do Prozac minus the placebo. So our proportion for Prozac should be 35 out of 49. The proportion for the placebo is 32 out of 44. And we want 95% confidence. And there we go. Now, notice with our confidence interval here, so if we interpret that, we're 95% confident that the true difference between the effectiveness of the Prozac recovery rate and the proportion of the placebo recovery rate, which means they just would have naturally grew out of their eating disorder without the use of the active drug, right, is anywhere between negative 0.2% and negative 20% and positive 17%. If you notice on this one, 0 is contained within that confidence interval. So because it's contained within the confidence interval, it's within the margin of error. So we think it's actually possible that there really is no difference between the active drug in Prozac and the placebo, the active placebo that we gave them, maybe a sugar pill or caffeine or something that made them feel like there was something going on when there really wasn't. Okay, so we would, based on this confidence interval, we would reject the null hypothesis, or sorry, we would not have enough evidence to reject the null hypothesis, so we would fail to reject. So how does the math work? All right. So we got two different samples. We have our Prozac minus the placebo. Those are the two proportions that we have times their Q naughts for this, P hat, Q1s, whatever, that whole thing, divided by the difference of their standard deviation, of their sample sizes. So that gives us a total standard deviation of 9.32. So to find our confidence interval, we take the difference between the two that we found, which was basically 0.13 and negative 0.13. So the placebo actually had a better recovery rate than the Prozac, the active drug, which is not good for the myth, as the Mythbusters would say. All right, so we take our best estimate, which is our largest sample size from our two treatment groups from our experiment. Take the difference between those two, plus or minus our critical value, which for 95% confidence is 1.96, times our standard deviation or standard error between the two samples, which was this value here. We multiply those together, giving us our margin of error, and we add and subtract it from it, giving us our total confidence interval, which, if you notice, is slightly different than what I had here. So I'm not sure quite what I did. I probably moved some decimals over, but this should be correct. Okay. All right, use your confidence interval to explain whether you think Prozac is effective. All right, since zero is contained in our confidence interval, we believe it's possible that there really is no difference between the effectiveness of Prozac, the active drug in Prozac, and the active placebo, and actually curing anorexia nervosa. So unfortunately, we failed to gather enough evidence to suggest that it is effective. So we would fail to approve this drug because not only do you have to show that it's safe, the FDA would have to show that it's effective, and that's actually worthwhile. So since zero is included in my confidence interval, it doesn't show that Prozac is effective. We failed to find statistically significant evidence that the effectiveness of Prozac. In fact, our placebo group had a higher recovery rate than our Prozac, which is not looking good. All right, based on my samples, you could interpret the confidence interval this way. I'm 95% confident that women taking Prozac deemed healthy between 20% lower and 17% higher than women taking placebo. And we notice that it is, the zero is within that. It's between a lower and a higher, so it's inconclusive. So part D, and suppose instead of constructing an interval, you conducted a hypothesis test. So for a hypothesis test, we do stat arrow over to test. Now, and it's a 2 proportion Z test. Now, the hypothesis test is based on the probability, the p-value is based on the conditional probability that the null hypothesis is true, meaning that there is no difference between the Prozac and the placebo. So keep that in mind. Now, our alternative hypothesis is since we're spending money on this drug, right? It's not just that it's different. We have to show that Prozac is more effective than the placebo, which would be a positive difference, meaning this is higher than that one, meaning it has to be greater than zero. In other words, Prozac is more effective than the placebo. That's what we have to show. So this is a one-tailed upper test. If we show the placebo is more effective than Prozac, that's not good for the myth, right? We need to show Prozac is more effective than the placebo. So base a conclusion based on that. So we're going to put it in the calculator. We want to show that our first proportion is larger than the second proportion. So we have Prozac and the placebo, and then hit calculate. Our p-value is 55%. So it's more than 50%. We need something that's in the top 5% or the or 1% or whatever alpha level we selected. So clearly this is not going to be statistically significant, and our z-score is actually negative. It should be positive, and it's less than 1, so it's going 1 standard deviation from the mean. So it's very, very common, almost what we would expect if we flipped a coin. So this is not really good evidence at all. So it looks like Prozac is not effective. They give you a difference in the sample proportions. This is the pooled sample proportion, by the way, which it'll do the pooling for you. Not like there was much of a difference between the two, and that's it. So say conclusion based on our confidence interval. So since our p-value was larger than our alpha level, we failed to reach that burden of proof with the significance level, the alpha level. So we failed to reject a null hypothesis in favor of the alternative. So we're going to have to stick with a null hypothesis, which is that there's not, we failed to reject a null because there's not enough evidence to suggest Prozac is more effective than our placebo. What alpha level did we use? Well, if we used a critical value to test it with 95% confidence, then what percent is going to be on each tail? So over on this tail over here, the upper part of the tail would be 2.5%. So we would have used an alpha level, which is kind of weird to draw that, but alpha is equal to 2.5. It's only weird because it's not part of like the Latin alphabet. It's Greek, and we don't use Greek letters very often. All right, if the conclusion is wrong, what type of an error did we make? Well, we failed to reject it when we should have, so that would have been a false negative, so that would have been a type 2 error. What are the consequences of such an error? Well, so that would mean that we missed out on the opportunity to offer to the world a viable treatment for anorexia nervosa. So that would be the consequence of the error. So we think Prozac was not effective, but it actually was. So we missed the opportunity to treat women with anorexia nervosa. All right, so that's all I have for you. Sorry the video was a little bit longer here, but hope you guys enjoyed it. Pulling's kind of cool. We're almost done. In fact, we just got 2 days of review, and then we have 2 more units left. The next unit, we're going to do all this stuff we've been doing with hypothesis testing, with proportions. We're going to do the same thing, but with t-test, which we'll get into with Gauss's distributions, but with proportions. Instead of proportions, we're dealing with means. So very, very similar unit to all the stuff we've been doing before. It's just slightly different. And all those videos are already uploaded, so that part's nice. And then we have a last unit, which I didn't do last year because it wasn't on the AP test, but it will be this year. But it just takes like 3 lessons. So we're pretty much done, and we'll be done, of course, in time to review for the AP test. So I'll see you guys later. Let me know if you have any questions.